First of all, a big thanks to Lilith at ENCCS for inviting us. My name is Erik Lenas. I'm a data scientist at the Swedish National Archives. And I feel very humble standing here in front of all this HPC experience. This is our first HPC project that I'm going to talk about, and it's the first for me personally as well. So I'm kind of close to the beginner spectrum, which is the users many of you are interested in, so it might be interesting anyways. Then Swedish National Archives and the digitisation of archival data. The Swedish National Archives has about 80,000 shelf meters of archival material, ranging from the 11th century until the present. And our digital archive consists of about 250 million scanned images of archival documents. So that's a lot of data, but you need to do something with that data as well. Just scanning the documents don't make them searchable. For running text documents, HTR and OCR is needed for a full text search, for instance. HTR is handwriting text recognition. And for forms and tables, it's more complicated. You need segmentation and layout analysis, and then you need to do HTR and OCR to transform the forms into searchable databases to be used by us internally or by the research. A few notes first on OCR and HTR. It consists of segmentation or text detection as a first step, and then text recognition. Models nowadays usually do text recognition on text lines. You need, if you got a running text page, for instance, you need to segment it into text lines first. And if you got a form or a table, you need to segment it into fields and then do text recognition. In 2015, an architecture for text recognition called CRNN, that is Convolutional Recurrent Neural Network, was introduced in a paper with a very long name. I'm not going to say it now. This architecture is still widely used, for example, in Tesseract and ABBY for OCR and in Transcribus for HTR. Transcribus is sort of a platform for doing handwritten text recognition. And the idea behind this model is to use a convolutional neural network to extract features from segments of images and then analyze them recurrently. Since 2019, several architectures for text recognition based on attention rather than recurrence and the transformer architecture have been developed in research and implemented in open source repositories. The usual advantage of attention versus recurrence, which is handling long-range context because it analyzes the whole sequence at once rather than recurrently, also applies to text recognition. Which architecture to choose is largely determined by the type of material you're going to analyze. If, for instance, you're analyzing running text, then CRNN might be good, but might be good enough. Like attention models are better, more robust to noise, and since they analyze the whole picture at once, and they are better at pattern recognition. So for instance, if your ground truth don't exactly match the characters in the image, then attention might be your choice because it can recognize patterns. Sorry. Okay. So indexing projects at the Swedish National Archives. The idea behind what we call indexing projects is to work with certain archival records that get a lot of requests from the public. For example, personal records or property records, and index them by some unique information that's there on the image, but that we need to interpret. For example, personal registration number or property name. By doing this, the scanned images become searchable by this information, and the relevant personal record or property record can be quickly looked up. And this streamlines our internal case handling. It's money effective, and it enhances the availability of the records. This started as a prototype project in 2021. The goal with this project was to investigate whether there is a general method and workflow for automatically indexing archival records with the help of machine learning methods. Our case study was the Church's Archives personal records. You see an image of it here on the right, and we're interested in the personal registration number in the top right corner, but also the names of the spouses, the children, for validation purposes and for building up information databases on persons. This is an example of a personal record. It's the project manager's Katarina Dahlgren's grandmother, so it's no GDPR problem. When we started this project, I was just starting out at the Swedish National Archives, and we didn't have an ML infrastructure in place. We didn't have access to any HPC environment. So we trained models on relatively small data sets and analyzed just a small sample of the records. The goal was arriving at a proof of concept, could this be of value? Could we make this valuable? And the results were really promising, and it led us to hypothesize a general method for similar indexing projects. It's a method that has a lot in common, of course, with like a general AI project. First of all, data collection, data for training and validation, databases for validation or predictions and spelling lists, etc. That step runs through all the other steps. Then image pre-processing and segmentation. We tried different techniques for image pre-processing, everything from simple binarization to more complex, cycle generative adversarial networks to remove noise. But the conclusion we arrived at was to choose a text recognition model that is robust against noise. That's better than doing complex image pre-processing. Then segmentation is a key step for all these projects, because we need to with good quality, we need to segment the images so that the text recognition can work with them. We need close bounding boxes, not disturbing text that's not relevant, etc. Then after the text recognition, post-correction, and eventual standardization, you can work with spelling algorithms, spelling lists. If you got context, it's possible to work with transformer models to do post-correction of text recognition. Then data validation and quality control. For indexing projects like this, when there's you need high quality of the resulting database. It's key with data validation because you don't want false positives in the database. And there's different methods for different archives. We work with databases for validation and that sort of stuff, databases that already exist. And the posts or the images or that don't get validated, they get sent to manual correction in a program written for that specific purpose. So the goal is not to get to 100%, but to identify the false positives and do them manually. So we went from the prototype project to implement it in a production project, in an actual production project. And that's where HPC comes in, and Lilith and ENCCS. Many requests from the public made to the Swedish National Archives concerns property records. And these requests require a lot of manual work by archivists, which could be greatly reduced if the scanned images were indexed by property name. We have approximately 18 million scanned images of property records, and 9 million of them are already manually indexed during a period that stretches 10 years. And this means we have all the training data we need for the remaining 9 million. This is the property record indexing pipeline in summary. We crop the head of the image where the property name is. We run an object detection model to make a bounding box around the property name. We run a text recognition model on that bounding box, cropped bounding box. We get a prediction, a standardized prediction. I'll talk more about that later. We link it against a validation database of valid property names that we got from another government agency called Lantmäteriet. We have other validation criteria as well. More about that later. We manually correct the non-validated instances in an indexing program, and then we save the results to an indexing database that is ready to use by a web app search application. For the object detection, we used Label Studio and an open source repository called Detection to train the object detection model. It was an architecture called Cascade RCNN. Detection is written by a group called Labs, and their idea is to take architectures from research, implement them in PyTorch, and write auxiliary code. It's a very good repo. They have lots of repos for AI vision and OCR as well. We used OCR for the text recognition as well. Training the text recognition model, then, we used our object detection model and the database for the already indexed property records. And we created the training set for the text recognition model. We train it on Vega on approximately 1 million images. And it was a Saturn architecture. It's an transformer architecture with a convolutional base, and it has 2D self-attention. So that makes it really robust against noise. And why did we choose attention rather than recurrence then? Here you see some images or property names with their corresponding ground truth. In the ground truth, or in the predictions, we're interested in 3 fields separated by semicolons. So we don't want a translation of what it says on the image. We want the standardized property name to result from it. And that means not doing, HTR or OCR character by character, but combining it with keyword extraction. By recognizing patterns in the input in the images and translating them into standardized property names. We validated the predictions against an existing database of property names to make sure the predictions actually are a valid property name. This is no guarantee against false positives. The prediction can be a valid property name, but the wrong property name. We applied various other criteria. I'll tell you a little bit about them later. And if the validation fails, the image gets flagged for manual control. So this is the manual correction. And manual corrections were made when link against validation database failed, or low prediction confidence. That's a pretty telltale sign that something went wrong. And we also have the region for the batch in our own databases. And when we link against the validation database, we also get a region. So we compare those regions, and if there's a mismatch, then it's probably a false positive. There's a trade-off between the number of hits and the number of false positives. Like if you do spelling algorithms on the fields against valid, if you do spelling algorithms, you get more hits, but you get more false positives as well, because it can correct the prediction to the wrong property name. Results then, I'm sorry about the ugly MATLAB Venn diagram, but I'll explain it. We evaluated the pipeline on a test set of 100,000 images spread over the data space. And the data space were locations in Sweden where the property records were made. And we got exact matches on just over 90% of the property names with a very low false positive rate. And below is a Venn diagram of the 233 batches the test set consisted of. Each batch consists of roughly 500 images. The bars represent 5% intervals. So the largest part is in the 95 to 100% interval. Most of the batches below 70% were actually errors in ground truth, that is, errors in the manual indexing. And we could also use this pipeline to correct those errors in the already indexed material. We haven't decided on whether to do that yet. Vega for training and inference then. We trained the Saturn model on Vega, and that enabled us to increase the scale of the resized images going into the model, and thereby improving the accuracy for handwritten text in particular, which generally requires more information than printed text. Running 9 million images through the pipeline on Vega took roughly 90 node hours. So that's not too much, actually. At a hit rate of 90%, this project saved us about 700,000 euros in manual labor costs. And of course, the indexing database gets created a lot quicker. That might not be a huge number, but it's our first HPC project, and it's a very important result for us because it shows value in these kind of projects. Okay, in the future then, ENCCS and Vega are opening up huge possibilities for us. And what we can do is, of course, more of the same. There are more indexing projects like this to be done, and which saves tax money and streamlines our case handling. We are also in the process of creating running text HTR base models for different time periods, with the goal of mass digitizing historical handwritten archival documents and making them available for research and public. We got a couple of crowdsourcing projects going on where volunteers are creating lots of training data for the 19th century, the 18th century, and we can use this training data to create large base models for interpreting historical text, handwritten text. We also want to improve our OCR pipeline and apply it on scale, use attention models there as well, train them ourselves with generated data. We would also like to create base models for segmentation of historical forms and tables. Historical forms and tables can vary a lot in looks and shapes, and we got loads of them. And we need to have, I think there's a need for base models that you could fine-tune on particular material and thereby getting a very good head start in those kinds of projects. And one possible future project is also to automatically transcribe the 19th century censuses. This project would be a part of an already existing research infrastructure called SWEDPOP, of which the National Archives is a part. And where we are doing right now, we're doing these transcriptions manually, and it requires a lot of work. And if we could do this automatically with good quality, as have been done in other countries, by the way, it would be save a lot of money. And also inspired by the Royal Library of Sweden, we've done experiments with training historical language models, like BERT, for instance, where we take, for instance, the Royal Library's BERT model, and we adapt it to historical texts. Training it from scratch is difficult because it's difficult to find those amounts of historical text, but adapting them is possible. Problem with this approach is evaluating the models. We're actually annotating a historical 19th century named entity recognition data set right now with the purpose of having something to evaluate these historical language models with. That's all for me. Thank you for listening, and big thanks to ENCCS, EuroHPC, and Viga. Thank you.